Today, we want to talk about trigonometric identities. Anytime you get stuck on a trig problem and you have no idea what to do next, there's probably some identity where you can replace some of the trig functions that you're looking at with some other trig functions, and the problem will start making sense. We've seen this a little bit because we were given some information in the problems on Tuesday about the angle with the secant. And we just immediately turned it into cosine so we could think of adjacent and hypotenuse. Turn it into one of the regular ones, not one of these weirdo ones like secant and cosecant and cotangent. So we want to talk about trigonometric identities. We're going to start with the reciprocal identity. This is how we take sine, cosine, and tangent and expand to cosecant, secant, and cotangent. So CSC is cosecant. And cosecant is the reciprocal of sine. So sine is 1 over cosecant. We get 2 for free, or we get a buy one, get one deal out of this. And that also means that cosecant is 1 over sine. We can describe this relationship by saying sine and cosecant are reciprocal. That's a little bit casual, but it gets the job done. Cosine and secant are reciprocals. So cosine is 1 over secant. And so secant is 1 over cosine. Tangent is 1 over cotangent. Tangent and cotangent are reciprocals. All 6 of these trig functions are important to you in your trigonometric future. That is the remainder of this class. Of these 6, the most important ones are sine, cosine, tangent, and weirdly, secant. Those are the top 4. I know there are some among you who can only do the complete set. You'd never be able to watch 3 out of the 4 movies. You have to watch the 4th movie. They're going to make another Indiana Jones movie, and we're all going to go watch it because we have to. We can't leave the set undone. So this applies to things that we already know about our trig functions. So, for example, we know that sine of theta is opposite over hypotenuse. And so that means cosecant of theta is hypotenuse over opposites. So if you recall, on Tuesday, we did a problem and we were given information about the secant, and we turned it into secant of theta. And we had information like secant of theta was 10 over 9. And we translated that into cosine of theta is 9 over 10. But we could, if all we wanted was adjacent and hypotenuse, 10 is hypotenuse and 9 is the adjacent. Because secant is 1 over cosine, the reciprocal of cosine. Furthermore, if we have a piece of information about a particular angle, say sine of 60 degrees is √3 over 2, then we can use this to find the cosecant of 60 degrees with the reciprocal. Sine and cosecant are reciprocal. Cosine and secant are reciprocal. Tangent and cotangent are reciprocals. One of the things that's a little bit sneaky is we also have a phrase called cofunction. Sine and cosine are cofunctions. But notice that cosine and secant are the ones that are reciprocal. So here's one class of identities. We like to organize our identities into different types. These are our reciprocal identities. There are ratio identities. These are how tangent is related to sine and cosine. Tangent of theta is sine theta over cosine theta. Question? It is. No, thank you. There, I just didn't finish writing the 3. Yeah, that's thank you. I know, -10 for me. So in the category of ratio identities, we have tangent of theta is sine theta over cosine of theta. You just got to remember that sine goes on top. We're almost never going to need cotangent. It's cosine over sine, especially once we get out of trigonometry. But cotangent has cosine on top, so that'll help you remember that tangent is the other one. Tangent is sine over cosine. This makes sense because if we take, because we have sine of theta is opposites over hypotenuse, and cosine of theta is adjacent over hypotenuse. And so if we write tangent of theta as sine over cosine, we'll have opposite over hypotenuse over adjacent over hypotenuse. And the 1 over hypotenuse can cancel out. If we don't like looking at the 1 over hypotenuse cancel out, we can see this is division. And so this is opposite over hypotenuse multiplied by the reciprocal hypotenuse over adjacent. And then the hypotenuses cancel out and we get opposite over adjacent. So if you're not keen on canceling out a 1 over hypotenuse from the top and bottom, just do the division, multiply by the reciprocal. Division is multiplication by reciprocal. This is why we focused on remembering our sines and cosines of all our angles going around the unit circle, because we could figure out what the tangent is with our ratio identity. So if we wanted to calculate, say, the tangent of 60, we can figure out, find the tangent of 60 by taking the sine of 60 divided by the cosine of 60. Sine of 60 is root 3 over 2. Cosine of 60 is 1 over 2. If you're uncomfortable canceling the 1/2 out of the numerator and denominator, you can just use the fact that division is multiplication by the reciprocal and take root 3 over 2 and multiply by the reciprocal 2 over 1. And tangent of 60 is root 3. So your primary focus on learning your unit circle should be on sine and cosine, the y coordinates and the x coordinates going all the way around the unit circle. You can work out tangents afterwards. Any questions? How's everybody okay? Yeah, we're trying to get that reaction, right? We don't want to have to think, we don't want to have to think about things. We just want to know stuff. So when I say tangent of 60, you want to immediately think of square root of 3. And in other combinations, if I say the tangent of something is square root of 3, that should trigger you thinking 60 degrees. You want to automatically think of 60 degrees. In the same way, I can ask, what's 7 times 8? It's 56. And then be able to turn that around. What's 56 divided by 8? That's 7. Knowing that relationship. It's a 2 out of 3 game. If I give you 2 of the pieces, you have to tell me what the third piece is. If I say 60 degrees and square root of 3, you should immediately think of tangent. The tangent of 60 is square root of 3. But if you forget, you can always build it out of other ones that you know. You want to look for the relationships in all the things that you know, so you can use the things that you know well to support the things that you don't know as well yet. How's everybody okay? It really looks very disgruntled today. You all look like this. Oh, you need to go get it. Is it still going to be there? Oh. You can go check if you want. I'll burn that bridge when I get to it. Now we're going to get into our super important identities. There are 9 Pythagorean identities, but you only need to know one of them. There's one of them that you have to have. Don't get to forget it. Sine squared theta plus cosine squared theta is equal to 1. If you like it, go in alphabetical order, cosine squared theta plus sine squared theta equals 1, then that's okay too. Since we're just trying to remember it, if you drop the theta part and just say sine squared plus cosine squared is 1, everybody will know what you're talking about. That's how the cool kids say it. If you like say theta every single time, people will think you are a nerd. Actually, if you just go around saying shit like this, people will think you are a nerd. Ask me how I know. I guess I didn't think of myself as easily identifiable as a nerd because I played D&D. So I'm like, you know what? I'm going to get a math degree on top of this. Please, why do you want to be so nerdy? I don't know. I'm also going to listen to prog rock. Like, all right, that's it. You're out. Get out. Well, it kind of, yeah. I don't watch math movies though. Like people be like, "Oh, did you see Good Will Hunting?" I'm like, "Oh no," but it has math in it. Like anything with math in it, I have to watch. Like, get the fuck out of here. Like there's that show Numbers, where the dude uses math to solve crimes, and it's like, "Oh, do you watch Numbers?" I'm like, "Oh no," but a guy uses math to solve crimes. I'm like, "Oh, that sounds kind of stupid." I don't know. I've never actually seen an episode of Numbers. Maybe it would be my favorite show, but we ain't going to find out because I'm not going to watch it. So I don't know. I'm not sure. Now, if the dude was using math to solve crime and the show was set in Middle Earth, then I might be watching that. It feels like the number of the ring. One ring to rule them all, but a countable infinity of a bunch of other rings. I don't know. So the important thing about the Pythagorean identity, sine squared plus cosine squared is equal to 1, is that this is a relationship between sine and cosine. Now, if we think about, we can see how this works. We know sine is in a triangle. Let's draw ourselves a triangle. Right triangle, because everything is right triangle right now. We've got an opposite, we've got an adjacent, and we've got a hypotenuse. The reason these are called Pythagorean identities is because they are based on the Pythagorean theorem. We know that in a right triangle, the sum of the squares of the legs of the right triangle is equal to the square of the hypotenuse. But we also know that sine of theta is opposite over hypotenuse. Cosine of theta is adjacent over hypotenuse. So sine of theta is opposite. Oops. So if we take our opposite over hypotenuse and adjacent over hypotenuse and drop them into this Pythagorean identity, it turns into the Pythagorean theorem after a little bit of algebraic manipulation. But sine of squared theta means we take the sine of theta and square it. The sine of theta is the opposite over hypotenuse. And cosine of theta is adjacent over hypotenuse. If we have a fraction raised to an exponent, we can distribute an exponent over a product or a quotient. So we have a fraction raised to an exponent, we can distribute the exponent to the fraction. So we get an opposite squared and a hypotenuse squared. Then we get an adjacent squared and a hypotenuse squared. Then if we just multiply every term in this equation by hypotenuse squared, we end at the Pythagorean theorem. So we can cancel hypotenuse squared out of the opposite and adjacent squared term, and then hypotenuse squared times 1. We end up at the Pythagorean theorem. That's why these are called Pythagorean identities. Sine squared plus cosine squared is 1 is the optimus prime of Pythagorean identities. This is the one that you have to know. We're not into transformers. This is the one Pythagorean identity to rule them all. All the other ones are subservient to this. But we do have to know variations of this theme. This one you cannot escape. A lot of times we want to see these solved for sine or solved for cosine. So two immediate variations that come to mind are that sine squared is 1 minus cosine squared, or cosine squared theta is 1 minus sine squared theta. We get this one just by rearranging. So just rearrange Pythagoras prime. I'm going to name this first one Pythagoras prime. There are other important variations of this theme. So if we got sine squared plus cosine squared is equal to 1, we have a tangent and secant version of this as well. So if we take our Pythagoras prime, if we divide everything by cosine squared, then we get the tangent and secant variation of the Pythagorean identities. Sine squared over cosine squared is tangent squared. Oops, I spelled plus wrong. Cosine squared over cosine squared is 1. 1 over cosine squared is secant squared. So this is the tangent and secant variety of our Pythagorean identity. This is our second most popular one. So I guess this would be like Pythagoras bumblebee. I don't know my transformers. Who's like the second ranking transformer? Is that just in popularity? I always get the idea that Bumblebee is like a kid transformer. Do they have children transformers? I don't know how transformers like make more transformers. Is anybody an expert on transformer lore? I think I need to know. Oh man, it's complicated. Anyway, this is the second one. Oh shit, is there more than one Optimus Prime? Stupid long running series. So just like we had with rearrangements of our Pythagoras prime, we can rearrange this one into two other ones. This one is solved for secant. This one says secant squared is tangent squared plus 1. But I can solve for tangent, and I can say tangent squared is secant squared minus 1. Or I can solve it for 1. And 1 is secant squared plus minus tangent squared. The hint that you're going to be doing stuff with Pythagorean identities is that the trig functions are being squared. As soon as you, at this point in your trigonometry career, when you see some trig functions being squared, you could be thinking, I bet some Pythagorean identities are in my future. I need to figure out how they're going to be included in this craziness. Of lesser importance is the cotangent and cosecant version of this. We do the same thing. Let's start with sine squared theta plus cosine squared theta is equal to 1. Whereas in the first one, to get tangents and secants, we divide it by cosine squared. Here we're going to divide by sine squared. So here we'll find out that sine squared over sine squared, we get 1. Cosine over sine is cotangent. 1 over sine is cosecant. And of course, we have the two rearrangements of this. So this one is solved for cosecant. We can solve for cotangent. Cotangent squared theta is cosecant minus 1. And we can solve for 1 and write cosecant squared theta minus cotangent squared. Nine different Pythagorean identities, all variations on Pythagoras prime. Sine squared plus cosine squared is equal to 1. How's everybody agree? You don't have to memorize these 9. Let's see, how many are 9, 10, 11, 12, 13, 14, 15, 16, 17, 17 so far. You don't have to memorize these 17 trig identities. You just have to remember these 17 trig identities. It's different. There's remembering them and there's memorizing them. Remembering them just means that you just know them. Memorizing them is actively trying to remember them. Think about your favorite song and think about the lyrics of your favorite song. Did you memorize those lyrics? Did you sit there like read it and then try to read it? Or did you just sing the song so many times you can't get it out of your head now? It's more likely the second one. Yeah, there's a lot of songs that kind of end up being that way, in which case I would argue they're not your favorite song. It's like that American Pie song. Like everybody's like singing along, but only in the chorus. No one knows any of the lyrics of that song. It's like blah, 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 until they go, the day the music died. They know that part because it leads into the chorus. And then everybody starts screaming, bye, bye, Miss American Pie. And they know that part, but then it gets to the next verse and they're like, oh, yeah, because you didn't know the lyrics. Any questions? So you might have noticed that these are all just printed places. Oh, we could have just read about these. But by writing them down in the notes, even though it's just replicating it, I was able to convince you all to write it all down. And that's the first step in knowing all these. I was able to subtly manipulate you into making you write them all down. Now, if I had said at the beginning, at the top of the class, like, oh, write these down, you'd be like, oh, no. It's called opposition reflex. You know what I mean? Like if I want my dog to go forward, I pull back on the dog, and that the dog has opposite reflex, right? So if you tell the students, write this shit down, they'll be like, oh, no. All right, well, don't bother writing this down. I'm just gonna write some stuff down here. You don't have to memorize it. You're like, oh, shit, it's notes. I gotta take notes. Do you know what I mean? You realize I'm using psychology on you. I'm manipulating you. I'm actually just building on the manipulation that you've been programmed with as children. If you were programmed with like, you have to take notes in class. And then that's it. That's the end of the instruction, right? Because as far as most people are concerned, taking notes in class is like, oh, write down what the teacher write down. So I'll have it for later. What am I going to do with this page? I'm going to scan it. I'm going to post it on Canvas. You'll have a copy of this page. But y'all were trained to be stenographers. So I'm like, oh, I'm going to write shit down. They're going to write it down. That's the first step in remembering it. See, it's so manipulative, this job. So manipulative. But it has this reputation for altruism. It's like, oh, I should trust my people. And he manipulates me with psychology. So I'm trying to make you learn math and against your will. I'm trying to invade your mind with mathematical knowledge. Man, if I could just like wave a wand at you and have you know trigonometry, you've got to know 100% I would do that. And then if I was the only person, like if every teacher could do it, then the secret would be out. But if I was the only teacher that could be like all trigonometry, acquiro, and boom, everybody knows trigonometry. I'd be like, all right, none of you can say how you learn trigonometry. We're going to pretend to go to class all semester and act like it's super hard. But really what we're going to be doing is just like checking in every couple of weeks. Like, oh, hey, everybody find out yet? And you'd be like, oh, nah, we're good. We're good. So, well, all right. They might come watch. So everybody go meet in the classroom. We'll be in the classroom. Someone comes off by. And so trigonometry. All right, they're gone. I'll see you next week. You just know it already. Do you know what I mean? That would be, I mean, I watched The Matrix and that's what my takeaway from The Matrix was. Oh, are you kidding me? They just like plug in and then they know shit. I don't know. Is the journey the adventure? I'm not sure if that's the case in math. Here's what you want to do. In chapter 2, you get your first round of trigonometric identities. You need to know how your identities are related. We need to tie this to stuff that what you've already know how to do, right? So with our Pythagoras prime here, sine squared plus cosine squared is equal to 1. I'll write it down again down here, example style. We've already seen if we do sine is opposite over hypotenuse, adjacent, cosine is adjacent over hypotenuse, that produces the Pythagorean theorem. We also know that, say, sine of 60 is root 3 over 2, and cosine of 60 is root 1 over 2. If we put these into the Pythagorean identity, we should get 1. So if we do sine squared of 60 plus cosine squared 60, sine is root 3 over, sine of 60 is root 3 over 2, and we square it. Cosine of 60 is 1 over 2, and we square it. Square root of 3 over 2 squared. Square root of 3 squared is 3, 2 squared is 4, 1 squared is 1, 2 squared is 4, 3 fourths and 1 4 is 4 fourths. So we're not getting new stuff. We're just finding new relationships in old stuff. But this is still just an extension of learn your unit circle all the way around. 0, 30, 45, 60, 90, 120, 135, 150, 180, 210, 225, 240, 270, 300, 315, 330, 360. Once we go around once, it's just copy it. Going around again. Learn your unit circle, going all the way around. Learn your cosine, going through one cycle. Learn your sine, going through one cycle. Vast amounts of data, different ways of visualizing that data, different relationships in the data. Good question. I'll go over, okay? He looks very tired. Let's pause the video. Let's take a quick break until Tuesday at 1 o'clock. I'm sorry for cutting things off a little bit early today, but I have some things that need to get done. And as the only child, I am the only one who can do that. It's just caught up with me. I'm like, oh shit, I don't have brothers and sisters to rely on. Right. That's it for today. I will see you on, that's it for today. That's it for this week. I will see you all back here on Tuesday. Sorry for leaving early. Everybody have a good weekend, and thanks for playing.